Okay, dear audience, welcome to my presentation. My name is Bong Kim, PhD candidate from the State University of New York, Stony Brook. And I'm really honored to present our work. Our paper entitled Private and Secure Post-Quantum Verifiable Random Function with NIZK proof and Ring LWE Encryption in Blockchain. Seeks to construct a verifiable random function scheme that stands firm against the quantum adversity in blockchain applications. We implement the secure randomness from a post-quantum ring LWE encryption with efficiency of a hybrid architecture, significantly reducing on-chain gas costs without sacrificing security. With 98.86% pass rate across the rigorous NIST test suite, our VRFâ scheme delivers a statistical proof of its robustness in randomness. Let me begin our presentation. To start, let me show you the roadmap of our discourse today. We will begin with an introduction to set the context of our work in the face of the looming quantum computing threat that endangers traditional cryptographic practices. Moving forward, I will unveil our contribution to this challenge, followed by an architecture overview of the solution we've proposed. We will delve deep into the mechanics of verifiable random functions and the Ring LWE encryption, key points of our strategy against the quantum vulnerabilities. Lastly, we will conclude with the security analysis and the randomness evaluation to validate our VRFâ scheme. To start, I will introduce a cryptographic component in blockchain technology known as Verifiable Random Function, or VRFs for short. VRFs are a special type of function that not only generate a pseudo-random number based on an input, but also produce a proof that this number was generated correctly without revealing secret key. Formally speaking, given a private key Sk and its corresponding public key Pk for any input X, a VRF produces an output Y along with a proof pi, such that anyone holding Pk, X, Y, and pi can verify that Y was correctly computed. In the blockchain applications, VRFs are indispensable. They ensure the randomness needed for secure and fair consensus algorithms, particularly in systems like Algorand with proof of stake. They are crucial for the applications like decentralized lotteries or task assignments. However, classical VRFs rely on certain mathematical problems for security, which are vulnerable to quantum computing attacks. Algorithms like Shor's pose a threat to these cryptographic underpinnings by potentially breaking the presumed hardness of these problems. Next, we navigate the intricacies of quantum computing and its implications on security systems. Let's embark by delving into quantum primers. Unlike classical computers, quantum devices harness the mechanics of the subatomic realm, performing computations with super high efficiency. This is made possible by representing data in qubits, which, unlike classical bits, can exist in multiple states simultaneously through superposition. Central to our discussion is Shor's algorithm. This algorithm provides an efficient way to factorize integers and computes discrete logarithms with fast speed, rendering traditional crypto systems like RSA and ECC vulnerable to attackers' exploitation. As we confront this quantum threat, the field of post-quantum cryptography leverages problems that remain intractable for quantum processors, safeguarding our cryptographic endeavors. However, current verifiable random functions, or VRFs, exhibit inherent limitations. They rely on the same computational problems that quantum computers threatens. Without quantum resistance, these VRFs could be compromised at some points, undermining the very essence of the verifiability and unpredictability we depend on. Next, I present to you the contributions of our paper. Firstly, we have architected a post-quantum VRF scheme of protection against the quantum threats by integrating decentralized identifiers, or DIDs, and utilizing ring signatures with NIZK proofs. We've established a new paradigm for off-chain validation that is both secure and efficient. Our second contribution is a smart contract-based VRF implementation that is powered by multi-party computation and the ring learning with errors problem. This approach not only enhances the security of the blockchain, but computational efficiency, drawing inspiration from the significant work of Click et al. In our commitment to transparency and reproducibility, we provide detailed descriptions of our Solidity and Python implementation. We meticulously outline our algorithmic methodologies and present a comprehensive complexity evaluation. Our paper delves deep into security argumentations, privacy explorations, and entropy assessments, ensuring that our Ring LWE-based VRFs stand up to the rigorous standards. And finally, statistical performance through NIST SP800-22 test demonstrates a 98.86% success rate, reinforcing the reliability and randomness of our VRF scheme. Next, let's explore the high-level architecture that safeguards the integrity and randomness within distributed networks. At the beginning of our process, participants with decentralized identifiers, or DIDs, engage in a multi-party computation, or MPC. Here, each MPC peer identifies by their unique DID, contributes a share denoted by S, and corresponding commitment C. These commitments are then recorded on the blockchain through transactions, forming the basics of our decentralized consensus. Once the seed is collectively generated, it triggers our off-chain components, which performs Ring LWE Encryption, a quantum-resistant algorithm ensuring the security of our VRF mechanism. The encryption process generates a VRF output, which is a random number that involves a verification process. Here, we employ Shannon's entropy and a non-interactive zero knowledge, or NIZK, proof to ensure that the output's randomness and integrity. This output is then returned to the smart contract, and then it can be utilized within the blockchain, as seen here as part of our distributed ledger technology. In essence, this architecture not only provides a verifiable randomness, but also enhances the trust and security of the participating nodes in a post-quantum cryptographic landscape. Moving forward, I will elaborate on the architecture of our VRF scheme, designed to strengthen the VRF in the blockchain platforms against the quantum vulnerabilities. At the heart of this architecture lies the integration of decentralized identifiers with the cutting-edge post-quantum security of Ring LWE Encryption. Our system starts with an on-chain multi-party computation, or MPC, where each participant collaboratively generate a seed through a smart contract. This is not just any seed, but one that's computed with efficiency within Solidity, Ethereum's program language. Once this seed is established on-chain, it triggers an off-chain blockchain listener. This listener, utilizing the Web3 protocol, activates our LWE ENC2 function, applying Ring LWE encryption to produce two ciphertext C1 and C2. But how do we ensure the integrity of this off-chain encryption? We employ a DID-based ring signature scheme inspired by the works of Franklin Zhang, combined with the Fiat-Shamir Heuristic and the Chaum-Pedersen methods for generating non-interactive general knowledge or NIZK proofs. The rigorous mechanism not only ensures the validity of the off-chain computations, but also fortifies the trust infrastructures of decentralized systems. Moving forward, let's delve into the evolution of verifiable random functions, which are the bedrock of many cryptographic systems, particularly in blockchain technology. VRFs are combinations of unpredictability and verifiability, acting as PRFs with the added capability of generating proofs for each output. This ensures that verifiers can produce the random numbers without knowing the private inputs that created them. The concept of VRFs was pioneered by Micheli and others in 1999 with a scheme based on RSA signatures and the application of the Gold-Ray-Levin hardcore bit transformation for achieving randomness. Following this, the field saw significant contributions from Naur and Langford, who developed an exponentiation-based PRF, and from Jukes, whose work explored particular group structures where certain computational DP-Herman problems remained hard, even as the decisional DP-Herman problems became easy. In the context of blockchain, VRFs have become indispensable. They are used in consensus mechanisms to ensure fairness and to prevent adversarial influence. However, with the advent of quantum computing, these classical VRF constructions are at risk due to their reliance on problems like a discrete logarithm, which quantum algorithm can solve. Recognizing this, recent research has sought to enhance VRF proof evaluation using admissible hash function architectures. Our contribution uses a blockchain-oriented VRF that employs multi-party computation and Ring LWE encryption, offering a quantum-resilient solution. Next, we explore the lattice-based cryptography and its role in protecting against the quantum computational threats. Let's dive into the foundations. Lattice L is a discrete subgroup within Rn formed by all integer linear combinations of n independent vectors. Visually imagine a multidimensional grid stretching infinitely in all directions. Formally, we express this as L of B sub 1, B sub 2 through B sub n equals the set of all summations from I equals to 1 to n of x sub I times b sub I, where x sub I is an integer. Cryptographic strength stems from the complexity of problems like the shortest vector problem and the running with errors problem. Transitioning to Ring LWE, we leverage the computational efficiencies of polynomial ring domains, which is practical in generating pseudo-random numbers and verifiable random functions, which are critical for blockchain technologies. The Ring LWE problem is simple to state, yet hard to solve. Given AX, A of X, X of X plus E of X, recover the secret S of X. This problem's quantum resilience has been underscored by research from Packard and others, affirming its robustness against quantum attacks. Next, I will introduce the non-interactive zero-knowledge proof, particularly focusing on the Chaum-Pedersen method combined with the Fiat-Shamir Heuristic. In the blockchain applications, we often need to prove we possess a certain knowledge of a secret without revealing the secret itself. The Chaum-Pedersen zero-knowledge proof allows us to do exactly that. Imagine having two public generators, G1 and G2, and needing to assert that for secret X, it holds true that H1 equals G1 to the power of X and H2 equals to G2 to the power of X without disclosing X. The prover starts by selecting a random value R and calculates the commitments of T1 and T2. If this were interactive, the verifier would now challenge with random challenge C. Instead, we use the Fiat-Shamir heuristic to non-interactively set the C at the hash of the commitment and additional context of public information. The prover then computes the response S and sends the proof pi consisting of T1 and T2 and S back to the verifier. The verifier recomputes C and checks if the equations G1 to the power of S times H1 to the power of minus C match Ti for I equals 1 and 2. Moving forward, I'll be presenting an integral component of ring signatures for our VRFâ scheme. In the pursuit of anonymity within blockchain transactions, we propose a DID-based ring signature scheme. This scheme is designed to validate members' participation without revealing their identity, offering protection against passive adversaries while aligning with a random oracle model for adaptive security. Let's delve into the system setup. Our ring R consists of participants, each with their own private and corresponding public keys within a prime cyclic group G. Given outputs C1 and C2 from Ring LWE Encryption, our VRFâ evaluation function takes an MPC-based seed and outputs a KK256 hash of the encryption result. When participant P1 wishes to sign the VRFâ output, they embark on a multi-step process involving randomization, hash derivation, and signature construction, culminating in the creation of a ring signature sigma and its proof pi. To validate the proof related to this signature, we employ our VRFâ verification function. It checks the integrity of each step, ultimately verifying the signature's validity against the computed hash. Next, I will introduce our approach for delegated key generation, or DKG, which is a pivotal in enabling secure off-chain ring signature without compromising users' private information. Our DKG protocol begins with each participant creating two distinct DID key pairs. The first pair is for executing tasks on the blockchain, while the second is exclusively for off-chain delegation, ensuring that on-chain activities remain secure and separate. Once generated, both public keys are committed to the blockchain. When it comes to the creation of the MPC seed, participants utilize their on-chain private keys. This collaborative process generates the seed that serves as the foundation for subsequent cryptographic operations for the VRFâ output. After the seed is established, a randomly selected participant encrypts their delegation key with the public key of the off-chain component. This encrypted key is then committed to the blockchain, where it awaits description by the off-chain entity. Upon receiving notification, the off-chain units decrypts the delegation key and proceeds to generate the ring signature. Next, let's explore the security analysis of our blockchain VRF scheme designed to stand firm in the quantum era. Our system is built on a strong foundation, the Ring LWE assumption, ensuring resilience against the quantum attacks that can easily break traditional cryptographic methods. We adhere to the quantum random oracle model, which postulates that hash functions like KK256 remain secure against the quantum adversaries, preserving the unpredictability essential for VRFs. The integrity of our VRF is twofold. Ring signatures that are impractical to forge without the correct key, and an MPC process secure against the tampering unless adversaries control the majority. We enforce 3 VRF requirements: uniqueness, a consistent output for each input, verifiability, outputs can be validated, and randomness, indistinguishable from a truly random sequence. Next, I will be discussing how decentralized identifiers are based on privacy and GDPR compliance within our blockchain architecture. DIDs grant each participant a self-sovereign identity, fundamentally enhancing privacy by allowing users to verify themselves without disclosing any personal information. This shift from centralized authority to individual control is a cornerstone of GDPR's privacy principles. Our private ring signature scheme takes this step further. When participants sign a transaction, their identities remain hidden within the group. They are verified not by who they are, but by the fact they belong to the trusted ring of participants. Moving forward, let's delve into the complexity analysis of our advanced VRF system, which is essential for understanding the efficiency of our cryptographic protocol in blockchain environment. Starting with temporal complexity, our MPC generation hinges on hashing operations, each with a complexity of theta k, and when combined with n participants, sums up to theta n plus k. Moving to the LWE ENC2 function, it leverages polynomial multiplication with a complexity of theta m log m, aligning with operations like entity and polynomial rearrangements, making it a cornerstone of our encryption process. Now, looking at space complexity, the key in consideration is the data structures used during computation. For MPC seed generation, the space required is proportional to the number of participants, yielding a complexity of theta n. The LWE function, being polynomial in nature, requires space theta n. To put this into perspective with typical values, for a hash size of 256 bits, 10 participants, and a polynomial degree of 1024, our analysis on a logarithmic scale indicates that the major computational tasks are manageable. Next, we explore the core of randomness within our blockchain architectures. As given in the slide, we quantify the unpredictability of our VRF according to Shannon's entropy formula. Okay. Next, I will share how we have evaluated the randomness of our Ring LWE system using NIST SP800-22 test suite. In our study, we applied 11 specially selected tests from NIST suite We meticulously chose these to match our data patterns, excluding tests that were not applicable to our system's output, thereby ensuring accuracy in our results. The findings were the majority of our tests reported, I believe, reported average p-values close to the ideal 0.5, signifying robust randomness. Overall, out of 176 tests, we observed only 4 failures, amounting to a pass rate of about around 98.86%. Next, I will be giving you a snapshot of our hybrid VRFâ system deployment. We've chosen Kanake, a personal blockchain, for deploying our smart contract. It's practical, allowing us to test locally without the cost of delays of the Ethereum main network. Now, each contract on the blockchain has a unique identifier. For ours, it's the 160-bit hexadecimal value, as you can see on the slide. This address ensures our contract is easily locatable and distinguishable on the blockchain. Eventually, as we conclude our presentation, let's recap the significant strides we've made in this paper. Our team has developed a Verifiable Random Function, or VRFâ, that stands resilient in the face of quantum computing threats. This achievement harnesses the power of Ring LWE Encryption, setting a new possible way for post-quantum VRFâ within blockchain technology.